Good evening, everyone. Welcome to the public lecture hosted by KIPAC. I'm just gonna clearly we're always running into these technical issues, but we will be getting them. All right, I'm going to start again.
Very loud.
Okay. Can I get this?
Sure. Yeah.
Sorry about that. Obviously,
We can hear you fine.
yes, it's for the Zoom people. Yeah, sorry about that. Okay, sorry, start again. Very sorry about that. Some of you might have seen that we have been here since 5:30, and this is what happened. All right. We are going to try again, and this time it's good.
It's very loud. It's pressing.
Okay. I will try to, yeah, speak with lower voice. Welcome everyone to the public lecture hosted by KIPAC, the Kaplan Institute for Particle Physics and Cosmology. My name is Sinan Du. I am the Outreach and Engagement Manager here at KIPAC, and I will also be the main host for this event. It is wonderful to see so many of you here in person. And we also welcome the online group of comparable size who is now watching the live stream. Some of you, if you have already followed KIPAC for a little bit, you may know that we try to feature public lectures on topics that are of your interest. And the beginning of the humorous has always been one of the most popular topics. So today we're very excited to actually feature this topic on the cosmic microwave background using the universe's oldest light to reveal its secrets. So before we get started, I would like to give a big shout out to the entire team who is supporting this event behind the scene. These include the front desk staff. Some of you may have already met. Of course, the AV tech team, and also Leon, who is helping me with the live stream. And because this is a hybrid event, we also have online chat moderators who are subject matter experts on this topic. And I will also have them quickly introduce themselves very quickly. All right, so first off, we have Yuka.
And yeah, hi guys, sorry. So my Zoom camera hasn't been working. But my name is Yuka. I'm a fourth-year grad student working on building a telescope called Bicep Array located at the South Pole. And this telescope is looking at something called the CMB, or the cosmic microwave background. And you guys will learn today all about what that is. So yeah, I'll be one of your moderators today.
Great, thank you, Yuka. And as some of you can see, even the in-room or Zoom technology sometimes can fail. And this is, all the difficulties we have been running into today, which is not typical. Next up, we have Chung.
Hi, hello, I'm Chung. I'm a postdoc, and I also work on studying cosmology and building CMB telescopes. I also work in the Bicep group.
Thank you. And last but not least, we have Abi.
Hi, everyone. This is Abi. Very happy to be here, one of the moderators online. I'm a postdoc here in the institute, and I do basically the kind of research which will be presented here today, on both on the theory as well as data analysis side. Outside of that, I enjoy playing and watching soccer, and also very recently have been enjoying doing my motorcycle rides in the area. Thanks.
Wonderful. Thank you all. So for those of you joining us online, you'll see the live chat on your right-hand side. We welcome all kinds of questions in there and also encourage you to engage in discussions. So most of the questions coming online will be answered by these chat moderators, and the remaining field will be saved for Federico to answer during the Q&A. And for all of you here joining us in person tonight, please save your questions until the very end, and Federico will be trying to answer everyone's questions, either officially or unofficially. So now it is my great pleasure to introduce tonight's speaker, Dr. Federico Bianchini, who is, looking very chill over there. Federico is a research scientist here at KIPAC and SLAC. His work focuses on using the CMB, or the cosmic microwave background data, both from space-based telescopes and ground-based telescopes, and try to interpret and analyze that data. And he is also part of several international collaborations, including the South Pole Telescope and also the CMB Stage 4 project, which he will also be talking more about tonight. So Federico got his PhD from the International School of Advanced Studies in Italy. And before joining Stanford, he was also doing postdoctoral work at the University of Melbourne in Australia. So tonight, he is going to be the storyteller of our event. And without further ado, let's welcome Federico.
Can everyone hear me okay? Awesome. All right, thank you so much for that wonderful introduction, Sinan, and for making this happen. That's it, sorry. One thing I forgot. My cursor, okay. Wrong screen. Sorry. There you go. Voila. So, all right. So thank you all for being here, either in person or online. I am thrilled to share with you some of the exciting research that we do here at KIPAC. And tonight, I want to tell you a story, one of, I think, the most intriguing stories that we as a species can tell, in fact. This is the story of the most ancient light in the universe. This light was emitted when the universe was only 0.003% of its current age. But this is also the story of how we build very sensitive telescopes and how we operate them in some of the strangest places on Earth to detect this light. This light is called the cosmic microwave background, or CMB for short, and has been traveling through the universe for about 14 billion years. And with that, it carries so much information about the early universe, okay? So it's a bit of a baby picture of the universe. And by analyzing it, we can understand how the universe kind of came to existence and how it has evolved, and potentially how we can know what the future might hold. So if all of this sounds very confusing to you, that's okay. That's very natural. Just sit back, buckle up, and enjoy the journey for the next 40 minutes or so. Hopefully, I'll be able to tell you something about this cosmic microwave background. Okay. I think I did. Is it picking up? No. It is on. Maybe I should. Okay, I'll try. Okay, so first thing first, I know there's some confusion out there, so I want to set the record straight. This is some job ad that I found online, and it says, make cosmology your career, training and supervision in hairstyling, blow drying, yada, yada. Okay, so If you're here for tips on, the latest hairstyles and that kind of stuff, I'm worried you're not in the right place. But if you want to, unravel the mysteries of the cosmos, then you're in the right spot, totally. Okay, so that's out of the way. But what is cosmology? Cosmology has the perhaps ambitious objective of studying the universe as a whole. We want to know about its structure, about its composition, and about its evolution. And so we as cosmologists are interested in answering some of the grandest questions in some sense, like, did the universe have a beginning? What does the future of the universe hold? We also want to know about its main building blocks, like what is the universe made of? What's its composition? We want to know about the shape of the universe, like is it infinite or does it wrap around itself? This kind of stuff. One thing that really drew me to cosmology is the fact that it really bridges the largest scales that we can possibly think of to the smallest one, to microscopic scales. And so if you want to understand, cosmology, you need to know a little bit about Einstein's general relativity, but quantum mechanics as well. And I think that's really cool. There's also one peculiar aspect, I think, about cosmology, and that is different from many of the other branches of physics. And that is that it is intrinsically observational. You cannot, recreate your own experiment in the lab. So in some sense, the universe itself is our laboratory. Okay, and so with that in mind, what we can do is basically just collect evidence, analyzing it, and piece together some story, pretty much like a cosmic detective would do. Okay, and the evidence that we collect typically comes in the form of light or photons. I will use these two terms interchangeably throughout the talk. And so this is why we want to build telescopes, right? Because these are nothing more than buckets for light. We want to collect them, and so we want to analyze this light. So I want to talk a little bit about light and its properties. I'll start with something that is probably obvious to most of you, but I think the consequences of what I'm going to say are still mind-blowing to me. So everyone knows, right, that the light has a finite speed, right? It's about 300,000 kilometers per second. Sorry for speaking international unit system. But so yeah, like I said, the consequences of this are, I think, mind-blowing, especially when put into cosmological scales, because what that means is that light takes some time, some finite time to cross distances, okay? And so take, for example, the moon, okay? This is about 400,000 kilometers away. So that means that the image that we see of the moon is about a second old, okay? We can even go further away, right? Or we can take our closest star, the sun, which is 150 million kilometers away. This is what we call an astronomical unit. And so if you do the math, you will see that it takes about 8 minutes for the light to leave the surface of the sun and to arrive to Earth. Okay, so that basically means that if the sun would go kaboom now, you wouldn't realize for 8 minutes or so, which is plenty of time. Okay, and so we keep going, right? Say for example, we can pick Andromeda, which is our closest galaxy, sorry, and that is about 90 trillion kilometers away. That's a lot of distance. And so if you do the math again, this turns out to be 2.5 years ago. So the light that is now reaching Earth was emitted 2.5 million years ago. So basically that light left Andromeda when the Australopithecus was walking on Earth. That's a long time ago, okay? And this is why, so you see that in cosmology, these distances become enormous very quickly. And so this is why we say, okay, well, Andromeda is 2.5 million light years away, right? Okay, and again, just to give you a sense of scale, this is Jade's GS-Z140. Okay, it's a funky name, but this is the most distant galaxies galaxy that we have detected. This has been detected with the James Webb Space Telescope, which some of you might know. And this is about 13.5 billion light years ago. So this is a very, very, big distance, and also a long time ago. And so the point that I want to make here is that telescopes are time machine, okay? The further away in space we look, the further back in time we're observing, okay? So maybe one question is, can we look back in space far enough that we see how the early universe looked like? But before we answer that question, let's recap some other properties of light. So light is an an oscillating electromagnetic field that propagates through space, okay? And so light is weird. It behaves both as a particle and as a wave. And as a wave, we can define a wavelength, which is basically the distance between like two peaks or two troughs. Light comes in all sorts of wavelength, and that's why we call it, the electromagnetic spectrum. And so you see, for example, we have light with very long wavelengths, like radio waves have, wavelengths of kilometers and even longer. And they can also have wavelengths comparable to an atomic nucleus, okay? And conversely, we can also define a frequency, which is just like the inverse of the wavelength. Our eyes are sensitive to this specific range of frequencies, right around here, which is called the visible light for, I guess, understandable reasons. Why is that? Well, the reason is we are very close to the sun, and the sun emits, is at the temperature, the surface of the sun is at a temperature of about 10,000 degrees. You see Kelvin here in Celsius, it's basically, especially for these high temperatures, pretty much the same. And so the thing is that everything emits light based of some kind of wavelength depending on its temperature. And this is just a fact of nature. For example, you might have seen that when you heat up a piece of iron, that will start to glow in the red. Okay, even we emit light. We are about at a temperature of roughly 300 Kelvin. So we emit in the infrared, and this is why you cannot see people in the dark, right? But if you had thermal goggles on, you could see them. Okay, so we can now talk about Doppler shift, which again, maybe some of you are familiar with. So Doppler shift happens when objects emitting waves, light, for example, or even acoustic waves, so sound, are in motion. It is exactly their motion relative to us that makes their wavelength stretch or compress depending the direction of motion, okay? And so this is, for example, what causes the changing pitch that you might hear when some ambulance is passing by. And so the siren will have a high pitch first, and then when it kind of passes you by, the pitch will become lower in frequency. And so again, this happens for celestial bodies too, right? So as they're traveling through space with some velocity and emitting light, you would see, for example, if they are moving away from you, okay, like in this top case, you would see that the wavefronts of the light that they are emitting become progressively more spaced. And so effectively that light will shift toward redder frequencies. And this is what we call redshift. Analogously, if this source is actually approaching you with some speed, these wavefronts will be closer and closer, meaning that the light will appear bluer. And so guess what? We call that blue shift. Okay, Doppler shift is important to understand the groundbreaking discoveries that really revolutionized our understanding of the universe about 100 years ago. So in the 1920s, two American astronomers, Vestos Slipher and Edwin Hubble, used optical telescopes to collect the light from galaxies. This is what we call spectrum. And they noticed something something interesting. So except for our very close neighbors, all the galaxies had their light shifted to the red. Okay, they all seemed red shifted, which, based on what I was telling you before, means that they all seem to be receding from us, so like moving away, which is pretty interesting. Not only that, so when Edwin Hubble actually plotted the velocity, actually these are not even velocity units, this is kilometers. So this is actually the plot from his paper. It's kind of wrong, but never mind. When he showed the velocity as function of the distance, he found this linear correlation, right? So the farther away a galaxy is, the faster it recedes from you, okay? Which is also what I'm trying to show with this graphic here. So again, further away galaxies are receding from you faster than those one close to you. Now, the interpretation that scientists came up with is that it is the whole universe that it is homogeneously expanding. And so when it expands, the light kind of stretches, and meaning that it will appear shifting to redder frequencies. So this expansion of the universe is actually something, it's a possibility that is allowed by Einstein's general relativity, although he was very stubborn and very reluctant to accept this idea of a dynamic universe. He eventually gave up, but yeah, he was very stubborn. And so a consequence of this expansion, in some sense, is that there is no privileged position. We all, even if you move to a different part of the sky, you will see this expansion. And so if you want to know more about this, we have some public lectures by Sandy Wan on the expansion of the universe and what's causing it, which I absolutely recommend you to check out. Okay, but so if the universe is expanding, then if I run the clock backwards, I should see it kind of shrinking and reducing in size. But as you probably know, when you compress a system, it becomes hotter, which is what I'm trying to show in this animation here. I'm sorry, it's very grainy. So these are some gas particles, right? And as you squeeze them together, they bounce, in the same unit of time faster. Okay, meaning that the gas is heating up, which is the same thing when you're inflating, like your bicycle tire, the pump will increase in temperature. Okay. And so the point that I'm trying to make here is that the universe, the baby universe, had to be very hot and dense. And given that everything that has a temperature emits light, it also had to glow. Okay, and so this idea that the universe was very hot and dense, so that all matter existed in the form of plasma, or like as a boiling soup of particles, was advanced in the 1920s by a Belgian priest called Georges Lemaitre, this guy over here. And in fact, he came up with this idea of the cosmic keg or the primeval atom, so that the idea that everything became from some kind of singularity. And if this sounds familiar to you, it's basically because this pretty much marked the beginning or the birth of the Big Bang cosmology as we know it today. Okay, so let me show you how the universe, the early universe looked like. So in this graphic, you see time that grows from left to right. So the early universe is here, over here. And you see that it was a boiling soup of, it was a plasma, right? So you have these squiggly lines, those are photons. Then you have some electrons, and it's mostly like hydrogen and the helium nuclei. Okay. So the photons are so energetic that basically they bounce off of these electrons and protons, and basically they don't allow them to combine together. Okay, and so the distance that these photons can travel is really limited. It's pretty much like it's like a fog. It's a cosmic fog. But eventually the universe expands. It cools down at around 380,000 years after the Big Bang. The universe is cold enough that the electrons can finally combine with protons, and this is basically what we call recombination. And so, in that moment, after that, the photons can simply, freely propagate through the universe, and eventually can reach our detectors, our telescopes. So, later on in time. Okay, and so in the 1940s, scientists were pretty good with doing nuclear physics calculations for, you can guess the reason. And so people like George Gamow right here predicted that if, the early universe was pretty much like, the interior of the sun, then the universe now should be filled with some leftover radiation. And they also predicted what this temperature should be. And it turned out to be of a few Kelvin. Now, let me fast forward to 1964 in Holden, New Jersey. So these two young astronomers, well, they don't look that young in this picture, but it's been taken, a few years later. So these are Arno Penzias and Robert Wilson. They were working at the Bell Laboratories, and they were using this very sensitive, at least for the time, horn antenna to detect microwave waves used for telecommunication. They were basically bouncing off balloons. And so while working on it, they picked up a strange noise at a temperature of about 3 Kelvin. And this is at a wavelength of 7 centimeters, or roughly 4 gigahertz. And it was very puzzling because it was everywhere in the sky. It didn't depend on the specific time of the year they were observing. And so they sat on this result for like more than a year. And at some point, they even climbed up inside the antenna, okay, and they scraped the pigeon's droppings, what they called a white dielectric material. But even after doing that, this excess of noise in their system was there, okay? And so they concluded that this is something that had to come from outer space, okay? And so around the same time, funny enough, Robert Dickey and his group at Princeton were actually putting together an experiment to detect that radiation that Gamow predicted about 20 years earlier, okay? And so when these two groups got together, well, they realized that basically Penzias and Wilson had scooped them. And so what Penzias and Wilson really detected was exactly this afterglow of the Big Bang, right? This radiation from the early universe that redshifted down to about 3 Kelvin, and it was now detectable in the microwave band of the electromagnetic spectrum, okay? So this is what we call cosmic microwave background. Let's break that name down. So it's cosmic because, like I said, comes from outer space. It is microwave because that's the portion of the electromagnetic spectrum where we detect it. And it's a background because it's something that comes from an early time, and so it has to come from far away. And it's so far away that it's basically behind everything we can see, behind all the galaxies and all the clusters of galaxies. Okay, CMB really represents a cornerstone of the Big Bang cosmological model, okay, together with the expansion of the universe. And it's basically for this reason that that Penzias and Wilson eventually went on and won the Nobel Prize in 1978 for their discovery. Okay, so let's try to imagine what Penzias and Wilson in the early 60s saw, quote unquote saw, because again, that's a radio telescope, so it doesn't really translate. So this is the Stanford Oval. For those of you who haven't been here before, I guess this is more for the people online. And it really looks like that for most of the year. It's sunny, it's nice, it's lovely. You should come. But if your eyes were sensitive to microwaves, this is what they would see. So they would see a remarkably uniform glow at a temperature of about 2.7 Kelvin everywhere in the sky, irrespective of where you're pointing your telescope, okay? And so this is really the baby picture of the early universe, okay? So this light originated 380,000 years after the Big Bang, and it's filling the entire universe. And just to give you, some numbers, basically in a given cubic centimeter, you have about 400 photons of such light. But this is not the whole story, because if I increase the contrast by about 10,000, this is what you see. So let me go back and forth. So you see these tiny fluctuations imprinted in the sky. And so these are fluctuations that are about, roughly 100 microkelvin. Okay, so in this room there are fluctuations in temperature that are much larger than that. Okay, and the whole universe had these small fluctuations back in the day. And so what you're seeing here are exactly the seeds of all the structures that we see today. So take, for example, one of these hotspots, or one of these, red-looking blobs. So again, like I was saying, that means that the temperature in that direction was higher. And so that represented an overdensity, like a slightly more dense region of the universe, which eventually will grow. And under under gravity will collapse and form galaxies. Okay. And so when you look at the CMB, like an image like that, you are really looking at waves that propagate in the primordial plasma. And so effectively, it's a tug of war between pressure and gravity, as I am showing here in this animation. So again, the yellow squiggly lines, those are photons. The points, those are charged particles like electrons and protons. And the gray thing, the gray blob is dark matter, which is something that I'll talk more about in a second. But for now, you just need to know that it only interacts with the rest gravitationally, okay? It kind of wants to pull in together. And so what you see here is exactly that. The gravity pulls all the matter into the overdensity, but at some point, the pressure of this photobaryonic fluid becomes larger, and so it wants to make the whole gas expand. And so it's back and forth, back and forth. So these are waves that propagate in this primeval plasma. Okay, and so this pattern of hot, cold spots represents, a snapshot of these cosmic ripples at the time of recombination. And so, like the ripples of fluid, the way for example, waves propagate depends on the composition of this fluid. And so you get an idea that basically we can learn about the universe composition by analyzing these waves in these CMB images or maps, as we call them. And there you go. And so the way we actually do that in a more rigorous and quantitative way is by breaking that CMB image that I showed you before into different scales, okay, and calculating what is called a power spectrum. Basically, we measure the amplitude of those waves as function of their size, of their wavelengths, okay, which is what I'm showing here. So this is the amplitude of these ripples, and this is the angular frequency. So this is the inverse of the size of those waves, meaning that the larger waves will be on the left of this plot, and the smaller waves will be on the right-hand side. And so you can think of it actually as a audio equalizer, right? So if you have something like some song with a lot of bass, you would have a stronger content of lower frequencies. So up here I am showing basically a number of points. Those are real, that's real data taken by different experiments, and I'll tell you more about this in a second. And as you can see, there is a remarkable agreement. So different people, different collaborations, different experiments looking at the sky, you'll see the same thing, okay, which is, I think, reassuring to some extent. In a way, this power spectrum of the cosmic microwave background, it's a little bit like a fingerprint, meaning that different cosmological models, different realization of the universe will look different, okay? And so there's a one-to-one correspondence between this power spectrum and what, for example, the universe is made of. And you can see how we can pretty much play a game where we compare our data, again, these points up here with the theory models. And here, for example, I'm showing you in white the best fit. So basically, that is the cosmological model that fit the best this set of data. And by doing that, we can come up with this cosmic pie chart, which basically gives you a breakdown of the composition of the universe, okay? So let me walk you through it. This might look a little bit surprising to some. So effectively, the atomic or baryonic matter, so the stuff that you and I are made of, and even the computer that you are using to watch this talk online is made of atomic matter, and that only accounts for about 5% of the total energy mass content of the universe. Okay, about 25% is in the form of this dark matter that I was alluding to before. And this is basically, as far as we know, well, it's dark because it doesn't interact electromagnetically, so we cannot see it. But what we know is that it interacts gravitationally, and this is pretty much how we know it's out there, okay? And it kind of clumps together, and it's very different, for example, from this remaining about 70% that is instead in the form of dark energy, which is probably like the craziest of them all, because it's something that has, I mean, we call it dark, but it's not related to dark matter. And it's crazy because it has constant density. So even if the universe is expanding, the density remains the same. It doesn't clump under gravity, unlike dark matter. And this is what we think is sourcing the accelerated expansion of the universe. This is something that I didn't tell you. So the universe is expanding, but it's not just that. It's actually, this expansion is accelerating over time. And we think that this is the troublemaker. And so, again, we have a bunch of KIPAC lectures on dark energy, dark matter, even on black holes. So I absolutely encourage you to go and check them out if you're interested. All right, so where do we actually go to measure this CMB? We have some requirements. We want little atmosphere as possible. And the reason for that is that there's a lot of water in the atmosphere, and water loves to absorb microwaves, okay? And so we don't want that. We want some place that has few distractions, right? So we know that, for example, Wi-Fi technology emits in the same band. So we want something that's quiet, and we want to go to a place where we can observe as much sky as possible. And so we have some options. The best one is, of course, sending things into space, right? Because there's no atmosphere, right? And we can observe the whole sky. The problem there is that it's expensive. You have very, stringent limitations in terms of size of the telescopes. Typically, the technology is a little bit older by the time they get to space. A somewhat intermediate option is balloons. So you build your telescope, you put it on some balloon up here. These are huge. These are like a football field size, okay? And then your telescope basically observe the sky from the edge of space. This is about 30 to 40 kilometers above Earth. Otherwise, you can go to the ground, right? And really, there are two main options you can choose. One is the Atacama Desert in Chile, and the other one is Antarctica. And the reason is that they are basically the best. These are deserts. And so these are great places for microwave observations. And so I want to tell you a little bit about my experience with the South Pole Telescope, which is South Pole Telescope, or SPT for short. This is a 10-meter diameter telescope at the Amundsen Scott station at the geographical South Pole. And it's been operating since 2007. So it observes in the millimeter wave band of the electromagnetic spectrum between 90 and 200 gigahertz. The last camera that's been installed on the focal plane, so you see light comes from space and then hits the primary mirror up here, and then there's a secondary mirror here, and then that's basically where the light ends up. And this is our focal plane. So these are detectors that we use to actually detect this light. And this is not your CCD camera in your digital camera, right? So these are called bolometers, and effectively are super sensitive thermometers cooled near 0 Kelvin. And again, we have a fantastic presentation about that on detectors if you want to know more about it. So again, why do we want to go there? The three main reasons, again, it's high. It's about 3 kilometers above sea level, so you have a thin air above your head. It's extremely dry because most of the water is in the form of ice under your feet. And then you have 1 month, one night that basically lasts for 6 months. And so this is that the atmosphere is very stable. And so you see here, for example, the telescope during one of these observations that scans the sky back and forth, back and forth. Okay, so this is a picture of the SPT collaboration at the face-to-face last June. This is about 100 people across mostly the US, Europe, and Australia. A bunch of very smart people across all career stages. And so let me just give you a sense for how great SPT is. So this is an image of the microwave sky taken by Planck, which is the most recent satellite that we sent into space in 2010, roughly. And so the moon is up there for scale. And this is exactly what happens when you look at the same patch of the sky with SPT. And you see that it is a much sharper image, right? It's more like you can see all the fine details. This is because, again, it has a better resolution and it has lower noise, okay? So it's more sensitive. Let me get rid of these large scale fluctuations so that I can enhance the details. And you can probably see that there are a bunch of things on this map, right? On top of, these black and the gray blobs. So we can detect two main things. So these white dots are typically galaxies of different kinds, radio galaxies, active galactic nuclei, and so on and so forth. So you can also do astrophysics on top of cosmology with this type of experiment. There's also something else. You have these shadows, which are clusters of galaxies. So these are the most massive bound objects that we have in the universe. So one thing like this can be even like 20 million light years across. These are huge guys, and we can see them in the CMB. Okay, so I've told you how the CMB gives us this image, this snapshot of the universe at recombination, 308,000 years after the Big Bang. But that's not the whole story, because these photons have been traveling, right? And they've been interacting with all the stuff, all the stuff that's in the universe. And one kind of interaction is actually gravitational lensing, which is the deflection of these CMB photons trajectories due to the intervening matter, okay? And so this is a cartoon picture, right? So you have some CMB image, and you see here some glass. This is the foot of a glass that's been put in front of it. And when the light from the background goes through the glass, it gets distorted, okay? And the same thing happens when light travels through the universe. And so not only we can detect these in CMB, but we can also learn about what's causing this distortion. So knowing, for example, what the glass is made of, okay? And we have also lectures on, KIPAC lectures on lensing, so you're absolutely encouraged to check them out too. Okay, CMB lensing, if you wanna know about gravitational lensing, you need to know a little bit of general relativity, which is something that we can definitely do in like 20 seconds. And so one way of looking at general relativity is a connection between mass and the geometry of space-time. And so as John Archibald Wheeler put it, mass deforms curves space-time, and in turns, space-time dictates how mass moves through space-time. Not just mass, even light, okay? And so what happens is basically that when that light is traveling in straight lines, but in a curved space-time. And so you have, for example, that these dark matter halos that host galaxies basically bend the space-time, and as these photons propagate, they perturb the trajectories of this CMB photon. Okay, so let me show you exactly what this is. So this is an image of the CMB. This is without lensing, and this is with lensing. So I'm gonna go back and forth. If you blink, you'll miss it. It's a very subtle effect, not like the glass that I showed you before. But so this looks similar, but in the lens map, you can actually detect changes in the statistics. And not only that, we can actually use these changes to reconstruct maps of the integrated matter distribution, okay? So in this case, you see a red spot. That means that there's more mass in that direction. And a blue spot means that there's less mass in that direction. We can also turn these images into constraints, for example, on the total matter density in the universe, okay? And this is using real data. So lensing can also probe particles like neutrinos, which are one of the least understood particles in the standard model of particle physics. And this is because lensing is sensitive to how structures evolve, and neutrinos affect how structures evolve. So for example, here I'm showing two numerical simulations of the matter distribution in the universe. Here we have massive massless neutrinos, and here they are massive. And so you see that they are qualitatively different, right? So massive neutrinos effectively smooth out this clustering of matter, and lensing is sensitive to that. And in fact, in the next 5 to 10 years, we'll be able to detect it. Okay, so I just wanted to quickly say that all of this research that I'm talking about is actually publicly available online. There are two main websites where you can check out our papers. This is Archive, and this is NASA ADS. Okay, so let me, like in the next 3 minutes, really wrap up with an outlook to the future. Like, what does the future of CMB hold? So, as I hope I have, conveyed, CMB has told a lot about the story of the universe, but there are so many questions, and hopefully the next generation of CMB experiments will really help us to, in our quest to understand the universe. Okay, these are some of the, outstanding questions. We have a pretty good estimate of the abundance of dark matter and dark energy, like I told you, but we really don't have a fundamental theory. Like, we don't know exactly what they are. And this is something that we would like to understand, right? Another thing is, we don't know what happened in the very, in the fraction of a fraction of a fraction of a second after the universe came to existence, okay? This is a process called inflation, and we want to know more about that. We don't know this neutrino mass, and hopefully CMB lensing will help us understand that. And also, we have very sensitive data sets now. And so different, for example, probes of the universe start to tell us different answers about some of these cosmological parameters. And we want to understand whether, is that a statistical fluke? Is that really new physics? Or maybe it is, or maybe it's just systematics, like instrumental systematics that we don't understand. And so the way to go about that is basically to, again, build new experiments. And we want to use more detectors, right? So we have lower noise. We want to use more frequencies, so more colors, so that we can do a better characterization of the signal. But we can also improve the systematics. And so in this direction, we have two main experiments that people here at KIPAC are really working hard on. One is the Simons Observatory, which is an array of telescopes in the Atacama Desert in Chile, with about 60,000 detectors. And even further down the line, in the 2030s, hopefully, we will have CMB stage 4. And this is going to be hopefully in the Atacama Desert and at the South Pole. And this is really, we think of it as the ultimate CMB experiment from the ground. Okay, so I will stop here. Thank you so much for listening, and many thanks to Sinan and all our moderators. These are my contacts if you want to get in touch, and this is our CMB group website here at Slack. So sorry, at Stanford. So if you're interested, check that out too. Thank you so much.
Great. Thank you very much, Federico. That was a lot to unpack in 40 minutes. So we are going to start the Q&A right now. If you have a question, simply raise your hand, and I will repeat your question so our online audience can also hear well. All right. So Malcolm.
Neglect the influence of the intergalactic medium. Do we have reason to believe that the CMB would look the same to all observers in the universe? Would it differ from place to place?
Okay, Federico, I'll just repeat that.
Thank you.
So I guess the question was whether or how the intergalactic medium had an effect on the ripples or the uneven maps, the hotter and colder spot that we were seeing, and if we are getting rid of that, are we seeing a smoother or even like a chunkier map of the CMB?
I think that's an interesting question. Again, we have only one universe to observe, and actually that in some sense dictates an intrinsic limit to the accuracy with which we can, measure its properties, or like that power spectrum, like the error bars that we showed. So in principle, if we go to some other galaxies far away, they would look, they would see the CMB, but they would see a different pattern of, those hot, cold spots. And in principle, like we could kind of ring them, and tell us what they see. We could actually improve, for example, the measurement of the CMB power spectrum, and in general, the accuracy with which we can learn about these cosmological parameters. So yes.
Great. And there's a great online question from Sunday asking, well, you talked about how far the CMB light was from us, right? And when that was emitted. How are you so sure? How do we know that information?
That's a good point. I mean, we know very accurately the temperature of the CMB, okay, which is about 2.7 Kelvin, okay. And so effectively, the temperature acts as it's also like a distance measurement, okay? Because we know that as the universe expands, it cools down, and like the wavelength of the CMB photon stretches. And so basically knowing how the universe, the electrons and protons combine together at the time of recombination, we can convert that temperature into an estimate of time, and that also gives us, for example, a distance.
Sounds like we're currently doing pretty robust work on that.
Yeah.
Right? Okay, great. All right, over there.
Also be able to measure the percentage of all the things studied with dark matter, dark energy based on the very temperature, or are there more useful ways of getting distances of the
That's a great question. So the cosmic microwave background is only one of the many observables that we have in the field of cosmology to learn about the universe. For example, again, you can look at the shapes and positions of galaxies, and that also is sensitive to, for example, the abundance of dark matter and dark energy. I talked about lensing, so the same thing happens, for example, with the shapes and of galaxies. So by studying the lensing of galaxies, we can also know about that. There's something called Big Bang nucleosynthesis, right? So the early universe was pretty much like, a nuclear fusion reactor. And so that's when the primordial elements like hydrogen, helium were formed. And so we know that theory very well. And we can basically, based on that, determine the abundance of the baryons in the universe, like, electrons, protons, and so on and so forth. So yeah, we have many handles on, and that's actually an interesting game to play, like combine, what we find from CMB, is that consistent with what we see with some other probe? And if not, that's when we have to think about.
Yeah, great. All right. Okay. Yes.
So we're in a spaceship or something, and like our target is galaxy. As we move towards the galaxy, would the galaxy start to like change shape as we see its evolution on?
Okay, so sounds like this question is related to like relativity, which is what we could explain in 20 seconds. So the question was, if we were on a spaceship and trying to head to a galaxy, as we're going there, are we able to see the evolution or any changes of the galaxy on our trip, if we were able to leave them?
I think I'd have to think a little bit about that question. Why don't you come down after the talk and let's address that offline?
Great, awesome. I'll take one more. Here.
Can you see the imprint of quantum gravity at the time of the Big Bang on the CMB, or do you need much more accuracy on the variations of the temperature?
Yeah, so the question was, were you able to see quantum gravity on basically imprinted onto the CMB map, right? Or would we need more precise measurement or telescopes to see that?
Okay, now that's a good question. So there's one point that I kind of alluded to towards the end. So I talked about inflation. And so again, this is basically a moment of superluminal expansion that we think the universe underwent really like at 10 to the minus 36 seconds after the Big Bang. So after the, singularity or whatever you want to call that. And so there are traces of this moment that we think are imprinted in the polarization of the cosmic microwave background, which is something that I didn't discuss tonight. So in the same way we can measure the intensity or the temperature of the cosmic of the CMB, we can also measure the polarization, which is basically kind of the direction in which this electromagnetic field oscillate. And this is very important because if inflation happened, then there will be a specific pattern in the polarization of CMB, which will be imprinted. And so we can basically look, when inflation happened, if it did, you would generate, for example, gravitational waves. And so that would give us hints about, whether, for example, like gravity is quantized and all of that. So yes, there are ways, and there are people here that are really working hard on addressing this kind of question. So possibly we might get there.
Awesome, thank you. And there is another question from Matthew online asking, you talked about most of the galaxies, they were receding from us and they should be redshifted. But how do we know that they're redshifted? And are there things that are blue shifted in the universe according to us?
That's a good question. Okay, so well, let me start from the last one. So the yes, there are things that are blue shifted in the sense that, for example, if galaxies are nearby and they are approaching us, the velocity would be such that is directed towards us, and so again that would give us a a blue shift effect. But the main point here is that systematically, as you go further out, all the galaxies are receding away from you, and not just that. The further away you go, the faster these galaxies seem to drift away from you. There was some other part. Did I miss?
Oh yes. So how do we know that all the galaxies?
So no, well, this is a question basically of how we measure these galaxy spectra. So effectively, a spectrum of light is just basically counting the number of photons at different frequencies or wavelengths. Okay, and so we know galaxies decently well, I think. And so, for example, we know that there are certain elements inside these galaxies, and so they will have a specific type of spectrum. Okay, so we know that spectrum. But for example, we know that a certain element would produce one line in this power spectrum at a given frequency. When we look at this galaxy spectra, for example, we see that line is a little bit to the right or to the left where we would have expected it to be, and so we can basically convert this difference in wavelengths between the one that we expect and the one that we measure. That gives us an idea basically of this redshift. That's actually how you define redshift.
Yes, and that's the magic of spectra.
Yes.
Yeah. All right, one last question from the in-person audience here. Let's see. All right, over there. Yeah.
So like how the James Webb Space Telescope has given us a lot of new data and new images to work with. Are there any moves to have something in the like CMB background? Can the James Webb be repurposed for that? Because I noticed a lot of ground-based satellites. Why not? Not with space.
So there have been.
Can you repeat?
Yeah, sorry. The question for people online is basically, please correct me if I'm wrong, is if we are thinking about putting together a space-based CMB mission And the answer is yes, as in it takes time, it takes money, most importantly. So there are proposals. For example, one that I can think about is called Lightbird. And I think it's a mostly Japanese-led collaboration that hopefully will launch a satellite at the end of this decade, hopefully. And again, and this actually goes back to what I was telling this gentleman, that basically the main scientific goal of that space mission would be to measure the polarization of the cosmic microwave background with the hope of detecting this signature from inflation. So yes, but it takes time and money.
Great. So on that note, we will wrap up the Q&A session. Let's give Federico and all right, so before we wrap up the event, I wanted to give everyone a heads up about what's coming up next if you're interested in joining us again. So if you have followed KIPAC for a little while, you may know that we are typically going to take a short break during the summer, but we are going to come back and resume in the fall. But in the meantime, if you wanted to participate in more public lectures or events, one of the KIPAC scientists, Chelsea Bartram, will be giving a lecture on dark matter radio. So how to make a radio to actually listen to dark matter and specifically axion dark matter. So that's on August 1st. And also in the fall, we are going to start our program with a public lecture that's about artificial intelligence and astrophysics. So that's going to be a pretty interesting talk on the interdisciplinary topic. And we will also have public stargazing nights at the student observatory on the Stanford campus, and also an event in Spanish called Noches Astronómicas, again, also on the Stanford campus. So we will share more details with the upcoming events. However, if you're interested in following us or to see what's new with KIPAC, feel free to follow us on social media and also join our mailing list. Of course, we would love to see you again, and let's try to bring everyone back again to the stage. So thank you everyone for attending. Really appreciate your time and attention. Tomorrow we will be sending out a follow-up email, including all the information that I have just introduced, and also with a very short survey. We wanted to know what you think about this event, what you wanted to hear about in the future, so we can organize more of this kind of event to your interest. So again, thanks everyone, and I hope everyone have a good night. Thank you.